Sol-gel method for nanoparticle synthesis, mechanisms, process control, and examples for cerium oxide and lithium iron phosphate nanoparticles. The Sol-gel method is a versatile wet chemical approach for the synthesis of inorganic nanoparticles with precise control over composition, morphology, and microstructure. This video presents an overview of the Sol-gel process, including reaction mechanisms, gelation behavior, drying, and thermal treatment. Furthermore, detailed experimental methodologies are provided for the synthesis of cerium oxide nanoparticles via a Sol-gel route and lithium iron phosphate nanoparticles using a combined Sol-gel and hydrothermal approach. The integration of these methods enables enhanced control over particle size, crystallinity, and electrochemical performance, particularly relevant for catalysis and energy storage applications. The Sol-gel process has emerged as a cornerstone technique in nanomaterials synthesis due to its ability to produce homogeneous materials at relatively low processing temperatures. The method involves the transformation of molecular precursors into a three-dimensional inorganic network through hydrolysis and condensation reactions. Compared to conventional solid-state synthesis, Sol-gel processing offers superior compositional control, reduced diffusion limitations, and the ability to tailor nanoscale features. Nanoparticles synthesized via Sol-gel routes are widely applied in catalysis, coatings, biomedical systems, and electrochemical energy storage. The adaptability of the method also allows integration with complementary techniques such as hydrothermal synthesis to further refine material properties. Fundamental principles of the Sol-gel process. Sol formation and hydrolysis condensation reactions. The process begins with the preparation of a homogeneous solution, Sol, containing metal precursors such as metal alkoxides or inorganic salts. Hydrolysis replaces alkoxide or ligand groups with hydroxyl groups, followed by condensation reactions forming MOM linkages and generating a growing inorganic network. Reaction kinetics are strongly influenced by pH, temperature, solvent polarity, and precursor concentration. Acidic conditions generally slow hydrolysis and favor uniform particle growth, whereas basic conditions accelerate condensation and may promote aggregation. Gelation and network formation. Gelation occurs when the growing clusters interconnect to form a continuous three-dimensional network. The gel point depends on precursor functionality, concentration, and cross-linking density. The structural characteristics established during gelation significantly influence the porosity and morphology of the final material. Aging, drying, and structural evolution. Post-gelation aging allows further condensation and structural rearrangement, improving network stability and reducing defects. Drying removes solvent to yield a xerogel, where capillary forces may induce shrinkage or cracking. Controlled drying techniques such as freeze-drying or supercritical drying help preserve porosity. Thermal treatment and crystallization. Calcination converts the amorphous xerogel into crystalline nanoparticles by removing organics and inducing phase transformations. Parameters such as temperature, heating rate, and environment determine crystallite size, phase purity, and defect structure. Controlled atmospheres can further tune properties such as oxygen vacancy concentration in metal oxides. Experimental methods. Synthesis of cerium oxide. Nanoparticles via Sol-gel method. Materials: cerium nitrate hexahydrate, ammonium hydroxide, urea, and deionized water. Procedure: a 0.2 molar aqueous solution of cerium nitrate hexahydrate was prepared and stirred for 30 minutes to ensure complete dissolution. Ammonium hydroxide was added dropwise under continuous stirring until the pH reached 10, resulting in the formation of cerium hydroxide precipitate. The precipitation step ensures complete conversion of cerium ions. The precipitate was collected and thoroughly washed with deionized water to remove residual ammonia and nitrate ions. Subsequently, the washed precipitate was dispersed in 200 milliliters of 0.1 molar urea solution to form a stable sol. The resulting sol was dried at 100 degrees Celsius for 2 hours to obtain a xerogel. Calcination was performed at 400 degrees Celsius for 3 hours to yield crystalline CEO2 nanoparticles. The process resulted in an approximate yield of 78%. To investigate size control, precursor concentrations of 0.5 molar and 1 molar were also employed following the same procedure. It was observed that increasing precursor concentration led to a decrease in nanoparticle size attributed to enhanced nucleation rates and limited particle growth. The sol gel-derived cerium oxide nanoparticles exhibit tunable size and high surface area, making them suitable for catalytic and energy-related applications. Control over precursor concentration enables systematic tuning of nucleation and growth dynamics. Synthesis of lithium iron phosphate via combined sol gel and hydrothermal method. Materials: lithium hydroxide, iron 2-sulfate, phosphoric acid, glucose, deionized water, nitrogen gas. Procedure: stoichiometric amounts corresponding to a lithium to iron to phosphorus molar ratio of 3 to 1 to 1 were dissolved separately in 50 milliliters of deionized water. Lithium hydroxide and phosphoric acid solutions were first mixed under magnetic stirring for 10 minutes. Iron 2-sulfate was then added gradually under continuous stirring, and the mixture was stirred for an additional 30 minutes until homogeneous. All processes were conducted under a nitrogen atmosphere to prevent oxidation of Fe2+ ions. The resulting solution was aged under nitrogen at room temperature for 24 hours, leading to gel formation. The gel was transferred into a Teflon-lined stainless steel autoclave and subjected to hydrothermal treatment at 190 degrees Celsius for 5 hours. After cooling to room temperature, the product was filtered, washed with deionized water, and dried at 120 degrees Celsius for 12 hours under vacuum. For carbon coating, the dried powder was mixed with 17 weight % glucose and sintered at 700 degrees Celsius for 5 hours under nitrogen flow, using a heating rate of 5 degrees Celsius per minute. For lithium iron phosphate, the combination of sol gel and hydrothermal methods significantly improves material properties. The sol gel step ensures molecular-level mixing and compositional homogeneity, while hydrothermal treatment enhances crystallinity and particle morphology. The resulting nanoparticles exhibit reduced size, 150 to 350 nanometers, compared to 300 to 500 nanometers for conventional methods, leading to shorter lithium-ion diffusion paths and improved electrochemical performance. Carbon coating further enhances electrical conductivity, addressing the intrinsically low electronic conductivity of lithium iron phosphate. Applications and challenges. Sol gel-derived nanoparticles are widely used in catalysis, coatings, sensors, and biomedical applications. In energy storage, nanostructured materials such as lithium iron phosphate benefit from improved ion transport and higher rate capability. However, challenges remain in scaling the process for industrial applications. Issues such as batch-to-batch variability, control of particle size distribution, and drying-induced defects must be addressed. Advances in continuous processing and in situ monitoring techniques are expected to improve reproducibility and scalability. In conclusion, the Sol gel method remains a powerful and adaptable approach for nanoparticle synthesis. The experimental demonstrations of cerium oxide and lithium iron phosphate synthesis highlight the method's versatility and its compatibility with complementary techniques such as hydrothermal processing. Continued optimization of reaction parameters and scale-up strategies will further expand its applicability in advanced materials and energy technologies.